Magnetoresistive random access memory is a non-volatile random access memory technology under development since the 1990s. Continued increases in density of existing memory technologies notably flash RAM and DRAM kept it in a niche role in the market, but its proponents believe that the advantages are so overwhelming that magnetoresistive RAM will eventually become dominant for all types of memory, becoming a universal memory. Description: unlike conventional RAM chip technologies, data in MRAM is not stored as electric charge or current flows, but by magnetic storage elements. The elements are formed from two ferromagnetic plates, each of which can hold a magnetization, separated by a thin insulating layer. One of the two plates is a permanent magnet set to a particular polarity. The other plate's magnetization can be changed to match that of an external field to store memory. This configuration is known as a spin valve and is the simplest structure for an MRAM bit. A memory device is built from a grid of such cells. The simplest method of reading is accomplished by measuring the electrical resistance of the cell. A particular cell is selected by powering an associated transistor that switches current from a supply line through the cell to ground. Due to the magnetic tunnel effect, the electrical resistance of the cell changes due to the orientation of the fields in the two plates. By measuring the resulting current, the resistance inside any particular cell can be determined, and from this the magnetization polarity of the writable plate. Typically if the two plates of the same polarity, this is considered to mean 1, while if the two plates are of opposite polarity the resistance will be higher and this means 0. Data is written to the cells using a variety of means. In the simplest classic design, each cell lies between a pair of right lines arranged at right angles to each other, parallel to the cell, one above and one below the cell. When current is passed through them, an induced magnetic field is created at the junction, which the writable plate picks up. This pattern of operation is similar to core memory, a system commonly used in the 1960s. This approach requires a fairly substantial current to generate the field, however, which makes it less interesting for low-power uses, one of MRAM's primary disadvantages. Additionally, as the device is scaled down in size, there comes a time when the induced field overlaps adjacent cells over a small area, leading to potential false writes. This problem, the half-select problem, appears to set a fairly large minimum size for this type of cell. One experimental solution to this problem was to use circular domains written and read using the giant magnetoresistive effect, but it appears this line of research is no longer active. A newer technique, spin transfer torque or spin transfer switching, uses spin-aligned electrons to directly torque the domains. Specifically, if the electrons flowing into a layer have to change their spin, this will develop a torque that will be transferred to the nearby layer. This lowers the amount of current needed to write the cells, making it about the same as the read process. There are concerns that the classic type of MRAM cell will have difficulty at high densities due to the amount of current needed during writes, a problem that STT avoids. For this reason, the STT proponents expect the technique to be used for devices of 65 nanometers and smaller. The downside is the need to maintain the spin coherence. Overall, the STT requires much less write current than conventional or toggle MRAM. Research in this field indicates that STT current can be reduced up to 50 times by using the new composite structure. However, higher speed operation still requires higher current. Other potential arrangements include thermal-assisted switching, which briefly heats up the magnetic tunnel junctions during the write process and keeps the MTJs stable at a colder temperature the rest of the time. And vertical transport MRAM, which uses current through a vertical column to change magnetic orientation, a geometric arrangement that reduces the write disturb problem and so can be used at higher density. A review paper provides the details of materials and challenges associated with MRAM and the perpendicular geometry. The authors describe a new term called pentalemma which represents a conflict in 5 different requirements such as write current, stability of the bits, readability, read-write speed and the process integration with CMOS. The selection of materials and the design of MRAM to fulfill those requirements are discussed. Comparison with other systems. Density equals, the main determinant of a memory system's cost is the density of the components used to make it up. Smaller components, and fewer of them, mean that more cells can be packed onto a single chip, which in turn means more can be produced at once from a single silicon wafer. This improves yield, which is directly related to cost. DRAM uses a small capacitor as a memory element, wires to carry current to and from it, and a transistor to control it, referred to as a 1T1C cell. This makes DRAM the highest density RAM currently available, and thus the least expensive, which is why it is used for the majority of RAM found in a computer. MRAM is physically similar to DRAM in makeup, although often does not require a transistor for the right operation. However, as mentioned above, the most basic MRAM cell suffers from the half-select problem, which limits cell sizes to around 180 nanometers or more. Power consumption equals, since the capacitors used in DRAM lose their charge over time, memory assemblies that use DRAM must refresh all the cells in their chips approximately 20 times a second, reading each one and rewriting its contents. As DRAM cells decrease in size, it is necessary to refresh the cells more often, resulting in greater power consumption. In contrast, MRAM never requires a refresh. This means that not only does it retain its memory with the power turned off, but also there is no constant power draw. While the read process in theory requires more power than the same process in a DRAM, in practice the difference appears to be very close to zero. However, the write process requires more power to overcome the existing field stored in the junction, varying from 3 to 8 times the power required during reading. Although the exact amount of power savings depends on the nature of the work, more frequent writing will require more power. In general, MRAM proponents expect much lower power consumption compared to DRAM. STT-based MRAMs eliminate the difference between reading and writing, further reducing power requirements. It is also worth comparing MRAM with another common memory system, flash RAM. Like MRAM, flash does not lose its memory when power is removed, which makes it very common as a hard disk replacement in small devices such as digital audio players or digital cameras. When used for reading, flash and MRAM are very similar in power requirements. However, flash is rewritten using a large pulse of voltage that is stored up over time in a charge pump, which is both power-hungry and time-consuming. In addition, the current pulse physically degrades the flash cells, which means flash can only be written to some finite number of times before it must be replaced. In contrast, MRAM requires only slightly more power to write than read, and no change in the voltage, eliminating the need for a charge pump. This leads to much faster operation, lower power consumption, and an indefinitely long lifetime. Performance equals, DRAM performance is limited by the rate at which the charge stored in the cells can be drained or stored. MRAM operation is based on measuring voltages rather than charges or currents, so there is less settling time needed. IBM researchers have demonstrated MRAM devices with access times on the order of 2 nanoseconds, somewhat better than even the most advanced DRAMs built on much newer processors. A team at the German Physikalische Technische Bundesanstalt have demonstrated MRAM devices with 1 nanosecond settling times, better than the currently accepted theoretical limits for DRAM, although the demonstration was a single cell. The differences compared to flash are far more significant, with write times as much as thousands of times faster. The only current memory technology that easily competes with MRAM in terms of performance is static RAM, or SRAM. SRAM consists of a series of transistors arranged in a flip-flop, which will hold one of two states as long as power is applied. Since the transistors have a very low power requirement, their switching time is very low. However, since an SRAM cell consists of several transistors, typically 4 or 6, its density is much lower than DRAM. This makes it expensive, which is why it is used only for small amounts of high-performance memory, notably the CPU cache in almost all modern CPU designs. Although MRAM is not quite as fast as SRAM, it is close enough to be interesting even in this role. Given its much higher density, a CPU designer may be inclined to use MRAM to offer a much larger but somewhat slower cache, rather than a smaller but faster one. It remains to be seen how this trade-off will play out in the future. Overall MRAM has similar performance to SRAM, similar density to DRAM but much lower power consumption than DRAM, and is much faster and suffers no degradation over time in comparison to flash memory. It is this combination of features that some suggest makes it the Universal Memory able to replace SRAM, DRAM, EEPROM, and flash. This also explains the huge amount of research being carried out into developing it. Modeling of 2D and 3D caches designed with SRAM, MRAM and other non-volatile random access memories such as RAM and PCM can be done using Destiny tool. However, to date, MRAM has not been as widely adopted in the market as other non-volatile RAMs. It may be that vendors are not prepared to take the risk of allocating a modern fab to MRAM production when such fabs cost upwards of a few $1 billion to build and can instead generate revenue by serving developed markets producing flash and DRAM memories. The very latest fabs seem to be used for flash, for example producing 16-bit parts produced by Samsung on a 50nm process. Slightly older fabs are being used to produce most DDR2 DRAM, most of which is produced on a one-generation-old 90nm process rather than using up scarce leading-edge capacity. In comparison, MRAM is still largely in development, and being produced on older non-critical fabs. The only commercial product widely available at this point is Everspin's 4-bit part, produced on a several generations-old 180nm process. As demand for flash continues to outstrip supply, it appears that it will be some time before a company can afford to give up one of their latest fabs for MRAM production. Even then, MRAM designs currently do not come close to flash in terms of cell size, even using the same fab. Alternatives to MRAM flash and EEPROM's limited write cycles are a serious problem for any real RAM-like role, however. In addition, the high power needed to write the cells is a problem in low-power roles, where non-volatile RAM is often used. The power also needs time to be built up in a device known as a charge pump, which makes writing dramatically slower than reading, often as much as 1,000 times. While MRAM was certainly designed to address some of these issues, a number of other new memory devices are in production or have been proposed to address these shortcomings. To date, the only such system to enter widespread production is ferroelectric RAM, or FRAM. Another solid-state technology to see more than purely experimental development is phase-change RAM, or PRAM. PRAM is based on the same storage mechanism as writable CDs and DVDs, but reads them based on their changes in electrical resistance rather than changes in their optical properties. Considered a dark horse for some time, in 2006 Samsung announced the availability of a 512 MB part, considerably higher capacity than either MRAM or FRAM. The areal density of these parts appears to be even higher than modern flash devices, the lower overall storage being due to the lack of multi-bit encoding. This announcement was followed by one from Intel and ST Microelectronics, who demonstrated their own PRAM devices at the 2006 Intel Developer Forum in October. One of the most attended sessions in the IEDM December 2006 was the presentation by IBM of their PRAM technology. Also seeing renewed interest is silicon oxide nitride oxide silicon memory. History: most of the following has been taken from RAMinfo website. 1955 a magnetic core memory had the same reading-writing principle as MRAM. 1988 European scientists discovered the giant magnetoresistive effect in thin film structures. 1995 Motorola initiates work on MRAM development. 2000 IBM and Infineon established a joint MRAM development program. 2000 Spint Laboratories' first spin torque transfer patent. 2002 NVE announces technology exchange with Cypress Semiconductor. 2003 a 128 kbit MRAM chip was introduced, manufactured with a 180 nanometers lithographic process. 2004 June Infineon unveiled a 16-bit prototype, manufactured with a 180 nanometers lithographic process. September Euro MRAM becomes a standard product offering at Freescale. October Euro Taiwan developers of MRAM tape out 1-bit parts at TSMC. October Euro Micron drops MRAM, mulls other memories. December Euro TSMC, NEC, Toshiba describe novel MRAM cells. December Euro Renesas technology trumpets a high-performance, high-reliability MRAM technology. Spintech Laboratories' first observation of thermal-assisted switching as MRAM approach. Crocus Technology is founded. The company is a developer of second-generation MRAM. 2005 January Euro Cyprus Semiconductor samples MRAM, using NVIP. March Euro Cyprus to sell MRAM subsidiary. June Euro Honeywell posts data sheet for 1-bit rad-hard MRAM using a 150 nanometers lithographic process. August Euro MRAM record, memory cell runs at 2 GHz. November Euro Renesas Technology and Grandis collaborate on development of 65 nanometers MRAM employing spin-torque transfer. November Euro NVE receives an SBIR grant to research cryptographic tamper-responsive memory. December Euro Sony announced the first lab-produced spin-torque transfer MRAM, which utilizes a spin-polarized current through the tunneling magnetoresistance layer to write data. This method consumes less power and is more scalable than conventional MRAM. With further advances in materials, this process should allow for densities higher than those possible in DRAM. December Euro Freescale Semiconductor Incorporated demonstrates an MRAM that uses magnesium oxide, rather than an aluminum oxide, allowing for a thinner insulating tunnel barrier and improved bit resistance during the write cycle, thereby reducing the required write current. Spintech Laboratory gives Crocus Technology exclusive license on its patents. 2006 February Euro Toshiba and NEC announced a 16-bit MRAM chip with a new power forking design. It achieves a transfer rate of 200 megabytes per second, with a 34 nanosecond cycle time the best performance of any MRAM chip. It also boasts the smallest physical size in its class Euro 78.5 square millimeters and the low voltage requirement of 1.8 volts. July Euro On July 10, Austin, Texas Euro Freescale Semiconductor begins marketing a 4-bit MRAM chip, which sells for approximately $25 per chip. 2007, R&D moving to spin transfer torque RAM. February Euro Tohoku University and Hitachi developed a prototype 2-bit non-volatile RAM chip employing spin transfer torque switching. August Euro IBM, TDK partner in magnetic memory research on spin transfer torque switching IBM and TDK to lower the cost and boost performance of MRAM to hopefully release a product to market. November Euro Toshiba applied and proved the spin transfer torque switching with perpendicular magnetic anisotropy MTJ device. November Euro NEC develops world's fastest SRAM-compatible MRAM with operation speed of 250 MHz. 2008, Japanese satellite, SpriteSat, to use Freescale MRAM to replace SRAM and flash components. June Euro Samsung and Hynix become partner on STT MRAM. 3. June Euro Freescale spins off MRAM operations as new company Everspin. August Euro scientists in Germany have developed next-generation MRAM that is said to operate as fast as fundamental performance limits allow, with write cycles under 1 nanosecond. 2009 June Euro Hitachi and Tohoku University demonstrated a 32-bit spin transfer torque RAM. June Euro Crocus Technology and Tower Semiconductor announced deal to port Crocus MRAM process technology to Tower's manufacturing environment. 2010 June Euro Hitachi and Tohoku University announced multi-level SPRAM. 2011 March Euro PTB, Germany, announces having achieved a below 500 picoseconds write cycle. 2012 November Euro Chandler, Arizona, USA. Everspin debuts 64 MB Street MRAM. 2013 November Euro Buffalo Technology and Everspin announce a new industrial SATA3 SSD that incorporates Everspin a Euro unregistered trademark S-Spin Torque MRAM as cache memory. 2014 January researchers announced the ability to control the magnetic properties of Korshal antiferromagnetic nanoparticles using only temperature and magnetic field changes. Applications. Proposed uses for MRAM include devices such as aerospace and military systems, digital cameras, notebooks, smart cards, mobile telephones, cellular base stations, personal computers, battery-backed SRAM replacement, data logging specialty memories, media players, book readers. See also. References. External links, mram-info.com, a clearinghouse of MRAM industry news, Everspin Technologies, manufacturer of MRAM memory, Spire, R. Meng, H. Pyraminegam, SN materials with perpendicular magnetic anisotropy for magnetic random access memory. Physica Status Salidi, Rapid Research Letters 5, 413 doi, 10.1002/PSS at 201,105,420. IBM Research MRAM by Richard Buettner, Ackerman, J. Applied Physics, Toward a Universal Memory. Science 308, 508 510 doi, 10.1126/Science 1,110,549. PMID 15,845,842. Allwood, D.A. Xiong, G. Faulkner, C.C. Atkinson, D. Petty, D. Cowburn, R.P. Magnetic Domain Wall Logic. Science 309, 1688 doi, 10.1126/Science 1,108,813. PMID 16,151,002. Wired News article from February, 2006, an EC press release from February, 2006, BBC News article from July, 2006, Freescale MRAM an in-depth examination from August 2006, MRAM the birth of the supermemory an article and an interview with Freescale about their MRAM technology, spin-torque applet an applet illustrating the principles underlying spin-torque transfer MRAM, new speed record for magnetic memories the future of things article.